Hello, my name is Rez, and I'm a professional game programmer, and I do electrical engineering as a hobby. So let's talk about this piece. So we hooked up these motors, and they have this whole piece in here that, for the technical videos, is really what I want to discuss. So let's read through this. It says both driven wheels receive the same torque, and therefore deliver the same power to the road, but the speed can be different, which enables cornering. Which is good, right? That's what I talked about last time. We can turn the thing. In the case of electric motors, both have the same voltage at the same speed. Each receives half of the battery voltage of around 4.5 volts. So in other words, they each receive 2.25 volts approximately. However, if one motor is slowed down with the fingers, its working voltage drops. The other motor then receives more voltage and rotates correspondingly faster. Not exactly. Yes and no, but not exactly. The motors require a current of around 100 milliamps when idling. If they're braked, the speed drops and the current consumption increases with the greater torque. Yes, that is correct. The battery voltage remains almost unchanged as long as batteries are still fresh. And then this goes on to talk about bad batteries and what happens if a motor is completely stopped and so on. And it's mostly correct. It's not entirely correct. Let's talk about what actually happens. If I were to just draw this a basic schematic of what we have. So we have our battery, and it comes in like this, and we have our motors like this. This is essentially our circuit. So we have motor and motor. Now I'm going to draw something slightly different here. I'm going to go like this, and we're going to come down here, and we're going to draw two resistors. I'm going to talk about two properties of electronics, series and parallel. In particular, I'm going to talk about series. Now, I drew this thing a while ago where we had this Ohm's law thing, where I had voltage, current, and resistance. And so these are connected through a multiplication symbol, and these are connected through a division symbol. So voltage divided by current equals resistance, voltage divided by resistance equals current, and so on. So this is just basic Ohm's law. Now the other side of this is if we have, say, let's make this a simpler number. Let's make this 10 volts in our just example circuit. And let's say these are both 1 kiloohm. What'll happen is the voltage, if I just put a meter here, a voltmeter here, and I put a voltmeter here, what are the values going to be? Well, this value is going to be 5 volts. This value is going to be 5 volts. It splits the voltage. So that's what the book was saying. That's what that little booklet was saying. That is correct. It will split the voltage. The current will be constant through this whole thing. You'll have a constant current through this whole thing. In this particular case, we could do the math. And the way that the math would work is we would take the sum of these two. So we'd say 1K plus 1K, which equals 2K. Then we use our Ohm's law. Voltage divided by resistance gives us current. So we would say 10 volts over 2,000. I'm just gonna cheat. 10 over 2,000. Okay, yeah, about 5 milliamps. So 0.005 amps, which is 5 milliamps. So that would give us, we'll have 5 milliamps going through this whole circuit. How does this work for motors? Well, the problem is I can't just take a meter and measure the motor. The motor is an inductive load. It doesn't quite use resistance in the same way. It uses something called impedance. And so the resistance is actually going to change depending on the conditions of the motor. It'll change whether it's under load, whether something is holding it, whether it's stalled. Its resistance changes the whole time. In fact, if you look up the motor, if we were to find the data sheet, and I don't know which motors these are, they don't tell me what the exact specs are, so I don't have a data sheet for them. But if we were to look up the data sheets of a motor, we could see that they specify a stall current. And here is one that I found just randomly. I just looked for a 5 volt DC motor. This is not our motor. I'm very sure this is not our motor, but this is just an example of what's here. So these are the technical specs. It operates at 5 volts. That's its best speed, or its preferred operating voltage. The no load speed, it will rotate at about 1,000 to 3,000 RPM, which varies. Its no-load current will be between 50 and 100 milliamps. Again, it varies. Its stall torque will be about 1.3 to 3 kilogram centimeters. Again, verified. All these vary by model. The stall current is somewhere between 200 and 500 milliamps. So what does that mean? It means back when in the previous day when I was just holding on to the thing and forcing it to stop, that is stalling. Stalling means you are forcing it to stop. It's the worst possible case for the motor. If you are in a position where you have to deal with that possibility, such as building robots, a lot of times that is a possibility. Someone can just pick up and stop the wheel. You have to be able to deal with that. So any component, if I were using this motor, I would ensure that any component would be able to handle this amount of current flowing through it. So I do the math and make sure that the, any resistors or anything that are in there, any, transistors can deal with this kind of current. So that is the basic idea. It's also got temperatures and stuff. I mean, this is pretty typical of a simple data sheet for something like this. So back here on the bench, what do? Well, the problem is that we can't just, as I said, measure this, at least not with an ohm meter. We have to measure it in a different way. We have to actually power up this circuit and measure the current flowing through the circuit. So we have our voltage of, in our case, 4.5 volts. And we have our current because we can measure it. And so then I can just take voltage over current and I can get the resistance, or in our case, the impedance, shown with a Z, of the motor. And I can do that if I just take one motor, I can do it that way. So let's do that. Let's test that and see what we can find. Okay, so here is our motor. It's hooked up to our little power supply through this guy. This is going to measure the current. So this is our current measured in milliamps. So I'm just going to turn this on. It's going to spike a little bit and then it'll settle. It's actually going to go a little haywire, but we'll see what it does. There we go. It settled around 97-ish. So we'll say it's about 97 milliamps, which I've written up here. So it's about 97 milliamps, and that's just free-flowing, everything good. Now the thing is if I turn this back on, and I just sort of like rotate this a little bit, there we go. We're at 95, 97. If I do this, it might be slightly different. There we go, now we're at 90. I mean, see, it's kind of all over the place. So these, it just depends on how much it has to exert in order to make this happen. If I just even touch it a little bit, just put my finger across it, it changes. So this is not an exact science here. Now let's do the other one. I'm not going to spend, I'm so worried that I'm breaking these. So I'm going to try this. I'm just going to hold it. Oh, I can't hold it. Okay, there we go. Come on. Ow. Oh man, that hurt. Okay, what was that? 667-ish? I'm going to call it 660. Now, all of this I'm running at, I'm running all of this at about I don't know if you can see that at all, but I'm running it at about 2.25 volts. Oh, come on, buddy. There we go. Running at about 2.25 volts. So this is what we'd expect each motor to receive, right? So if we come back out here and we do the math on this, so 2.25 volts, right? We divide this by 0.097. Okay, so we have 2.25 volts divided by 0.097. That gives us about 23.2 ohms. So here we have an impedance of 23.2 ohms. But for the stall current, it's very different, right? So we're going to have, it's the same thing, 2.25. But in this case, we're going to divide this by our stall current of 0.66. That's going to give us about 3.41 ohms. 3.14 ohms. We have to, 3.41, other way around. Okay, so this gives us a little something to work with. Now let's use these values up here. Now I'm going to change these values. I should have color-coded these better, but I didn't. So for green, we're going to say what these are if these are non-stalled. We have 23.2 ohms. We have 23.2 ohms. I would expect it to split here, and I expect the total current of the circuit to be 23.2 times 2, so what, 46.4? So divided by 46.4, I'd expect it to be about 97-ish milliamps, which is what we're getting here at the 2.25. So there we are. So I would expect the total current to be 97 milliamps when we actually measure with both of the meters. So Ohm's law is holding up at 2.2 volts and so on. Now, what they assert is that if I stall one of these motors, what's going to happen? I'll do the stall in, I don't think blue's going to show up. A little bit. I'll do it in red. We stall this motor, we're going to get this value, 3.41 ohms. This one's going to stay the same at 23.2. But now we have a very different prospect. Now we have, what do we have? 23.2 plus 3.41 gives us 26.61. 26.61 gives us a total current of about 170 milliamps. So in this instance, we'd have about 170 milliamps if I stalled this motor down here. With 170, so that's actually why this motor goes faster. It's not necessarily because we're going to drop more voltage here, and we are going to drop more voltage here. In particular, I would expect, let's see, that would be 23.2 divided by, whoops, I screwed that up, 23.2 divided by 23.2 plus 3.41 gives us that equals about 0.87. So we're going to multiply that by our 4.5. I would expect us to have about, across here, about 3.92 volts. I would expect across here to be, whatever the difference of that is. So 4.5 minus, 3.92 gives us about 0.58. Doing the math, this is what I would expect. Now, I don't actually expect this because in theory, practice and theory are the same, but in practice, they are not. So I don't actually expect this to happen, but what they're saying, the thing that I'm saying is wrong, the thing that I disagree with, is they're directly saying that because the voltage drop is higher, it's going to draw more current. That's not actually correct. It's not because the voltage drop is higher. It's because this impedance drops, thus dropping the overall resistance, the overall impedance of the entire circuit, thus drawing more current. That's why. The voltage isn't changing. The voltage across the entire circuit isn't changing. Just because there's a higher voltage drop here doesn't change the total current through the circuit. It's because this guy is dropping so low. This voltage drops, this voltage is going to raise, but really it's about the overall impedance dropping. This thing drops 20 ohms out of the circuit. So now we have, it's not twice the current, but it's approaching twice the current. Hence why they say it'll run close to full speed. I would expect it to run close to full speed, assuming 4.5 is full speed. I'd expect it to run close to full speed as well. Not because of this, or not because of this voltage, but because of this. That's why. So that's what we'd expect. And now we're at the final piece of this, which is where the rubber meets the road. I have 3 meters set up. I've got the experiment with a bunch of stuff hooked up. Basically, it's this circuit. So I've removed the LED and everything like that. It's just the 2 motors as we've had. It's these 2 right here in series, just as normal. And I've just hooked up meters to them. So this left meter, I should say the meter on the far left is the current. This is the current through both of that series circuit, those 2 meters. I'm going to expect this to read about 97 or so milliamps-ish. This left meter, this middle meter here is for this guy on the left. This right meter is for this guy on the right. They're voltage meters. So they're going to measure these voltages. I would expect them to be at about 2.25, and I'd expect them to obviously be about the same. Now, they may not be exactly the same, but I would expect them to be pretty close. So let's just turn this on and see what happens. Okay. They're not quite the same. They're One's 2.32 and one's 2.15-ish. So they're a bit off, right? They're not quite the same, which is fine. It's, I'm sure within tolerance. Again, I don't have the data sheet for this. We're at a pretty almost spot on 97 milliamps. Slightly less, but we're about the same. Now, when I stall this, I'm going to stall this one here. This is, again, I'm treating it as this bottom one. I'm going to expect that this guy is going to plummet. This guy is going to skyrocket. I'm going to expect it to go to somewhere in the neighborhood of 4 volts, somewhere in the neighborhood of half a volt, somewhere in the neighborhood of 100 and whatever I said, 70-ish. Might not be quite that. We're a little bit low, so maybe, it'll be less than that probably. So let's stall it. Yep, we're about 4.1. We're about a little less than half a volt on the other side. We're at 116, 17-ish milliamps total. We'll turn that off. And so close. The current was quite a bit off. The voltages were pretty spot on, but the current was quite a bit off. Now, the thing is, I expected the current to be more closer to 170, maybe even as low as 150. It was off by much more than that. Why is that? Well, device tolerances, device heating, like all these things can come into play. These are non-linear devices. With non-linear devices, you really kind of have to measure them or do much more complicated math to figure out what's going on. I did expect the current to be higher, but it wasn't. And I guess that's about it for the technical video. I just wanted to talk about how that voltage kind of splits and about how really it's about the current that's being drawn through the thing, not specifically the fact that this thing is dropping more voltage. The dropping of the voltage is a side effect of the resistance, the impedance of this guy getting lowered, which thus increases the overall flow of current. So of course, if you have more voltage, you are going to have more current, but it's not exactly about the drop of voltage across this thing. It's very specifically about how much current is flowing through the circuit. If I limited the amount of current flowing through the circuit, we get a very similar result. Yeah, that's it for the technical video. I will see you all tomorrow.